everybody, and welcome to the presentation. It's so good of you all to attend. This is now being live streamed. It's inexplicable what's happening. It's unbelievable, and we're hoping it's going to get you involved with the amazing world of quantum physics and quantum computing, remembering that anything quantum is smaller than an atom. So you are made of quantum particles. You are a quantum object. So's your computer, so's everything. We're not atomic, we're subatomic. And strange things happen at that level. Yeah, I'm just going to quickly show the agenda. Let me just give you a quick introduction to the teams one at a time. We'll start with Vic. If you can just say a few words, Vic. Hello, Vic. How are you?
I'm fine, thank you, thank you. I'm happy being a part of this game. Looking forward to once we start over here, then maybe we can spread around for other places in Malaysia. Okay, and nice to meet all of you. Yes, that's it.
Thank you very much, Vic. Now you are a quantum programmer. At least you're really getting into it, aren't you?
Yeah, I'm just getting my hands on into understanding the quantum programming. I'm very excited when I heard your effort that you would like to bring it down to younger students. So
Yeah.
that's what I'm doing here on virtual robotics in my country. So I would like to do it along with quantum education as well.
Now here we go to Team Zimbabwe, led by the president of One Quantum Africa, Lorraine Mashiri. Lorraine, how are you all there? How many have you got?
I have three of my friends here. Hopefully the fourth will join us. We have Noku, Rachi, and Tino. And I'm happy
Excellent.
to be...
Give us a wave, ladies. Give us a wave in the background. Yeah, you can. Now listen here, Lorraine. You've got 4 women there. I want no cheating, okay?
No cheating.
Well, you all look honest to me, so that's going to be great. Do they know the rules yet, or are they waiting for Anne?
I've briefed them on the rules, but definitely they'll be looking forward to hearing it from Anne again.
Hello, Anne. How are you?
Hello, Eamon. I'm well, thank you.
Excellent. Now, you're going to explain the rules of the game, aren't you?
I will definitely give it a go. Yes.
And Anne, you're the education and training manager at CSIRO Pawsey, and there's a lot happening there, isn't there?
There's a lot happening at Pawsey. Yeah, Pawsey is a supercomputing research center, one of Australia's 2 Tier 1 centers, and there is a lot happening in supercomputing and quantum at Pawsey. You're absolutely right.
And the wonderful Amanda. How are you, Amanda?
Hi, I'm really well, thanks, Eamon. How are you?
No, you're not really well, are you?
Well, apart from having COVID, yeah.
Yeah.
I've got a positive test result today, so everyone's got their. I'm very safely distanced from everyone through Zoom.
Yeah, the beauty of technology.
Oh, yeah.
Okay, Anne, we're right on time. Take it away. You've got, how long do you have? Oh, it's 5 minutes, but take as long as you want.
5 minutes, I should be able to cover that, Eamon. Thank you. So you should have with you a pen or a pencil, and as well as a piece of paper. And your referee should have a die or a dice, right? So this little, I have a tiny one here. And you'll need 2 people to play the game, and then 1 referee. And what we're going to be using are things that look like this. They are 3x3 grids. So the goal is to have a row and a column have the same number at an intersection. So it sounds pretty easy, right? So if this row is picked and this row is picked, then this would be the intersection, and we want that to be a 0 or a 1, both going up and up and down and going across. Now, that sounds pretty easy, but the tricky part, the fun part, is the chance. So that's where the dice comes in, and that's where the referee comes in. So what you do is one person who's got the row, who's ever going to be doing the row, you're going to be using zeros and ones, and you need a even number of ones in a row. So that could be no ones, or it could be 2 ones. Now, player B or team B is going to take the columns, and they are going to have an odd number of ones. So that could be 1 1, or it could be 3 ones that they can do. And what you want to do is you want to strategize with your partner to say, okay, we're going to get 1 row and 1 column only. How do we make sure that that intersecting piece is going to have either both have a 0 or both have a 1? Now, you don't know if it's going to be the first, the second, the third. That's where the dice comes in. I, as the referee for my team, am going to roll the die, and that will be, the first roll of die will be which row is selected. Now, the first person will they'll do their row, but the second person doesn't know. And then I'll roll the die again, and they'll do they'll do the column, whichever number. So if it's a 1 or 2 or a 3, they'll do either the first, the second, or the third. Now, you can talk with your partner of the row and the column to strategize and collaborate beforehand. But once we close it and we roll the die, you cannot talk, and you don't know what the other person is getting. So that's where the game of chance comes in. And that's where you'll either stay in the game if you do get that 0 or the 1 the same, or you'll leave the game if they're not the same. And I think I've covered it. Eamon?
I think you covered it too as well. Well done indeed. Yeah, thank you very much for that. Vic in Malaysia is saying, yeah, he's got it. He says he doesn't have the dice, but look, you can make up a number between 1 and 3. It's all got to be random. You can.
I thought of that too. You could have a little bag, right?
Mhm.
And in your bag, you could have little pieces of paper, 1, 2, and 3, and
Yes.
then or multiple 1, 2s, and 3s. Always the same: 2 1s, 2 2s, 2 3s. Crunch them up, put them in there, and then pick one out, and that's your random number.
Well, very creative, Anne. No wonder you're an education and training manager. No,
that's fun. It's a game.
That is exactly right. There are 4 teams from around the world: Australia, India, Malaysia, and Zimbabwe. I'm going to go to each area. I'll start with Vic, simply because you're top of the list. Hello, Vic. You seem to be happy with all of the rules?
Yes, Eamon, I'm clear and happy, yes.
Excellent. Okay, I'll put you backstage for the moment. Team Zimbabwe, are we okay with the rules, Lorraine?
Yes, we are okay with the rules. I guess okay with the rules.
Yes.
Excellent. Okay.
I'm gonna play along with my own little number generator and play against myself.
What a good idea. You're not going to play with the dog?
I always did enjoy like solitaire and that kind of thing. So
Yeah.
I'll be fair. I'll be fair.
Yeah, good. I trust you implicitly. Oh, wow. Isn't it wonderful? Okay, look, I just wanted to take a few minutes before we actually start playing the game. And, this is just a game, but what you're going to witness tonight is unbelievable, because the game is impossible to win. And at the end, I will show you that by using quantum computing and a quantum strategy, you'll actually win every time. So I'll just bring on the panelists. We'll have a discussion for about 20 minutes.
Hi.
Hi, everybody. So we may start with Anne in WA. And what's your opinion of being in education and training? What's your opinion of playing computer games helping you learn something?
I think any kind of gaming with the right objectives and the right outcomes that you're targeting are fantastic ways to learn, because it's fun, right? You're going to remember something that you enjoy and that you laugh or that you have fun with, and it's engaging. It's much better than learning something rote. Yeah, if you embed it within a game, it's more memorable, definitely.
Look, I absolutely agree. And I would think that this is 100-fold better when you're doing a quantum game, because not only are we going to teach a principle, as you do with classic games, we are going to show something tonight that's impossible classically in the universe we live in. It's impossible. Yet we are going to show how using quantum games, using quantum forces, we can literally do the impossible.
Actually, I'm totally agree with Anne that the game is because I used to get involved with younger students. So the easiest way to kind of catch their attention and get into for me to explain something new. So using game as a platform has been very, very helpful and very effective, I would say. So that's why when I heard of these zeros and one games compared to qubit game, which Google came up before, this looks more user friendly. That's what I would say.
I just thought, yeah, how big is quantum computing getting in Africa? Now, you're the president of One Quantum Africa, so you're spreading the word as much as you can. What's the vibe over there?
The vibe is good. The response is good, especially when you start with using games. I really feel it's an amazing strategy because I managed to have my friends who are in a different field altogether, and they're interested in curious, and they're joining us today because it's the approach for them to learn quantum is through games. So I think it's an approach that I really want to adopt more across Africa because I mean these are proof that my friends are proof that it works. So I'm excited to see how games do work in helping people learn a concept. It's a fun way of learning, and you might not even need to know the basics to just learn because it's just about understanding the rules of the game and understand the principles being used as we go.
And now, if we can go to Amanda. Amanda, so you're basically, you and I have been talking for, I don't know, 2 years or something about getting quantum and the concepts out there. Can you tell me where, what angle you're coming from as a interested parent?
Well, I work with families and educating around having a healthy, balanced lifestyle. And part of that is a model I'm developing around an activity code and how to help kids have that balance. And I just think the way that you are translating an absolutely complex subject such as quantum computing, and you're breaking it down to engage and really support youth coming on board with what is going to be the biggest disruptor like in their lifetimes is really is fantastic, and it's very inspiring to me and the scientist in me. But yeah, I just, along with my passion and like my purpose of helping people with their healthy hearts and minds, I think this quantum science is fascinating, and for people to be able to be brought along this journey and learning together, I think is I think you're doing a great job.
Oh, well, thank you very much. And beautifully said. Yeah, it is mysterious, it's fascinating, and it is the real world. I have a bit of a thing when people say to me, "Oh, what a wonderful world we live in," I say, "Yeah, what do you think of quantum entanglement?" They say, "Never heard of it." And I say, "Well, you don't even know how wonderful the universe is. You think it's beautiful with the bit you know. If you knew what the amazing forces that happen in the quantum world, it's unbelievable." But tonight we're going to, oh, sorry, you did say one thing which I thought was really relevant. You were saying it is a complicated area, and it is. I'm going to do my best later to explain how the quantum can win it every time. But before we get to that, I want everybody to play the game and lose.
I'm also fascinated at how this sort of noughts and crosses looking game is going to teach us about quantum computing.
Yeah, well, you will. Let's in fact, what a great segue into starting the round. So look, let's start round one. You may start.
All right. For the first round, Team Zimbabwe, we are done. We are ready. So the students won this round. The red number gave me their combination. The red team gave me their combination as 111. I got 101 from the blue team with 3 and with the red team on the third column and the blue team on the second row. So for that round, the students won.
Okay, the blue team, row 3, as what I've just put in the private chat there, is a 110. And column 1, the red team got 111. So basically the intersection, same number 1.
Okay, thanks, Vic. Let's now go to Anne in Australia, Team Australia. Oh, Anne, what's this?
Oh.
I know. Look, so this is what we did.
Yeah.
And you have one teammate sticking the head in the corner there. 0 1 0 1 0 and 0 1 1. Sadly, they did not. Yes, they did not match.
Let's go to Team India. Now I'm expecting an accent here as well. So
sorry about that.
That's okay.
So mine was similar to Anne's in that.
No.
Is that backwards? Is that backwards for you?
It is, but that's okay.
Oh,
We can see.
okay.
I can see a great big cross and
Yeah,
a 0 and 1.
0 1 0 for the odds, and 0 1 1 for the evens meant that they didn't match. So we're out.
And look, we're going to say a quick hello to Joanne. Joanne's joined us late. Here she is, Joanne Spooner.
Sorry, I'm late.
That's okay. That's okay. Joanne's a physics teacher in West Australia, but we'll have a chat later, Joanne. Okay, has anybody got can anybody comment, even if you lost? Because it's all the roll of the die, which is what I'll be getting to later. But can anybody comment on a strategy that they used? I go to Zimbabwe because you were strategizing from the, if that's a word, from the beginning. And Lorraine, what strategy did your ladies use?
So for this round, the strategy they used, initially they discussed 2 strategies, but for this round, with the look of things, the strategy they used was using the most number of ones. So that meant for the red team, they used 3 ones, and for the blue team, they used 2 ones. So that increased their chances.
I had the zeros at the beginning of both of my numbers and the ones in the middle of both of my numbers. So that gave one. I suppose that's only really two out of the 9 chances of winning.
There was actually no particular strategy. I just requested them just choose whichever random combination comes to their mind. So let's see if it intersect. Okay, good. Otherwise, it's okay.
Yeah, so just completely random, which is a strategy in itself. Anne, did you want to say something?
We had the human factor intervene. So we had a similar, or I heard them talking a similar strategy as Team Zimbabwe. But then the second person, Team B, thought they would rethink it on their own after the strategizing was done.
Oh,
the human factor intervened.
Let's start with round 2, and that's only Malaysia and Zimbabwe. I'm afraid the others have to listen in. So let me bring everybody back, and then I'll do a bit of explaining. Okay, now let me explain what was going on there, basically. You see, spoiler alert, there's always one square where you can't have a 1 or a 0. Now, if you look at the bottom right-hand corner, you can see if we put a 0 in there, then it violates the row, because the row will be 1, which is odd. And if we put in a 1, it will violate the columns, because the columns will then be even, and the columns have to be odd. So you will win 8/9 of the time, because 1 in 9 times the intersecting square on average will be where that question mark is now. Your chances of winning are actually, in the game that we've just played, was 8/9 to the exponent 4. If you were playing 24 rounds, you've got a 1 in 1,000 chance of winning. So using all the classical strategies, you win about 89% of the time. After 4 games, you've got a 62% chance of winning. And every time you play, it's 8/9 times 8/9 times 8/9, etc. So your chances of winning decrease every time by 1/9. I've got questions coming in from the audience. Here's one, but I'm telling you that using a quantum strategy, we can win every game forever. If you played 100,000 games, you would win every one of them. Now, we're all having fun and it's a game, but what is happening defies all logic. Quantum application developers are already writing industrial quantum software that beats all logic. And we're beginning to understand things like DNA, sequencing, photosynthesis, bird migration. Trust me, this is all down to quantum physics. Can we just talk about how unbelievable it is that we can play a game like this and write a quantum program that can make us defy logic and win every time? Vic, with your programming, do you have any insight, to add?
Because I believe since we are working, because I noticed someone asked the question how anything or anyone can get it right every time forever, right? So you see, sometimes when we do some simulation, like in my virtual robotics, we play on the ranges. Okay, sometimes we try with the short range, we try with the long range, and then we do some charting. How well things works in relative to the change of ranges. So that's why I believe I've also put a comment in the private chat, because probably since you're working on 3x3 grid, okay, I maybe later would like to simulate what if my students play on 4x4 or 5x5. What would be the probability later on if they, playing this game?
But you're a physics teacher in WA.
Yep.
I'd love to hear your comments.
Having something like this happen in your class, it will be amazing, especially with all the different groups that are going on in the class. and they'll get to see it happen lots of times and how they are going to lose. That's what I want to see. I can't wait.
Yeah.
It's a bit mind-boggling, really, and the fact that there's computer programs that are programming ways that the world is going to operate that we don't even actually understand with our logical minds. So that's kind of like, so on one hand, we're programming all these computers to do these magic things, but we don't actually understand. So that to me is like quite an interesting concept.
I used to be a software developer, and everything about writing code is very logical, down to the last semicolon. Absolutely. I don't understand how a program can be written that's not logical.
Yeah, so I would say it's not intuitive to a classically trained mind. However, it is intuitive to students who are not yet classically trained. They get it. They sense that there's something right about it, but they can't explain it. It resonates with them. So to them, I believe it is intuitive that, of course, this works. But if you're classically trained, it's going against logic.
I'm just enjoying the conversation. I didn't have a comment at the moment.
Well, from what Anne was saying, that someone just feels like it was a possibility, I suppose I have that equanimous or inquiring mind. And as you know, I've got interest in sort of consciousness and the mystique of the world and spirit to a certain extent. And so therefore, that I can't prove. That the whole, in the yogic philosophy, there's a concept around the chakras and the energy centers of our body. And it's not nothing that's been written down or proven, but it's through experiential. So I guess there is a certain amount of voyaging into understanding.
And with, you know, as you know, I'm very scientific. I don't believe in anything that can't be demonstrably proven. But I've always said, I've said it to you many times, but I've always said, if science can't give an answer, then don't start saying what it isn't. So it may, something weird's going on. By the way, Einstein said it wasn't. Einstein in 1932, it's a very famous EPR paradox he did with two other authors. And he said, there is nothing funny going on here. It's just our knowledge isn't good enough. And to cut a long story short, he was proven wrong in 1966 by an Irishman, Professor Bell, who proved something weird is going on. Yeah, I'm going to play for you the answer that has come from CalTech and the Google AI people. So that will, you know, if you have no knowledge of quantum physics at all or quantum computing, you will not understand this explanation. But I want to play it anyway, so you'll start becoming familiar with terms and things like that. Now, I will explain after this video, I will explain what is happening in as basic a way as I can, but that means I have to explain quantum entanglement and a thing called superposition, a Hilbert space, a phase shift, a quantum gate. And we're not going to do that in 10 minutes, but I want you to, you know, you're not going to follow me, but I want you to be intrigued as you are. But let me play the video first.
You probably already figured out that even with the best classical strategy, the game of zeros and ones can't be won with certainty. In fact, the more times you play, your odds of winning get exponentially worse. But things are different if we're able to see the world through a lens that brings the quantum realm into focus. If you can access it, you can unlock powers that make the impossible possible. For example, you can win this game 100% of the time every time you play. Researchers at places like CalTech and Google are learning how to build new machines that act as our lens into the quantum realm. We call these machines quantum computers. Since we don't yet know how to access the quantum realm directly, we can use quantum computers as a bridge between the two worlds. Computers enable us to represent and transform information about the physical world as a series of states, 0 or 1, on or off. We call these bits. Quantum computers take us a step further. They enable us to represent multiple realities simultaneously as a series of quantum bits, both 0 and 1, on and off, at the same time. We call these qubits. So, how can the quantum realm help you win every time? By using qubits, the two sides can write their answers in a way that guarantees they always win, even when no communication between them is allowed once the game begins. Here's how it works. Before the game starts, each side writes down the 4 combinations that satisfy their even-odd constraints. For blue, that means these 4 rows with an even number of 1s, and for red, it means these 4 columns with an odd number of 1s. Now each side uses their own set of 3 qubits to store their valid answers, where each qubit represents a single square. Combining these 4 times 4 combinations results in 16 possible realities that the quantum computer can store simultaneously. At this point, if the referee checks the group's answer by asking the quantum computer to reveal the state of the 6 qubits, the referee will find themselves in one of those 16 realities. But not all of them lead to winning combinations for the group. While each row is even and each column is odd, the intersecting square observed by the referee also has to match. Let's assume for now that the referee observes the middle row and the middle column. In this case, the middle squares in each row and column have to match. Out of the 16 possible realities, the blue and red side only want to keep the 8 where the row and the column match. To do this, we can use an ability that's unique to the quantum realm known as quantum entanglement. This ability enables the two sides to link the state of their middle squares so that they always match. After this procedure, the only realities that remain in the quantum computer are the 8 winning realities. When the referee asks the quantum computer for an answer, they find themselves in one of those 8 realities with equal probability. They have no control over which of the 8 realities, but it doesn't matter which one, because all 8 lead to a win for the group. But what happens if the referee chooses a different row and column? The 8 winning realities for the second row and the second column no longer guarantees a win. Can the blue and red sides update the state of their qubits in the quantum computer without communicating to still guarantee a win? The group needs to store one more piece of information in their qubits. Let's look at the 2 realities where the row is in the 0, 0, 0 state. For this row, there are still 2 options for the column. Remember that blue can only see the qubits in their row, so only the 0, 0, 0, and has no way of knowing the state of red's column. We can fix this using another important aspect of quantum states, but we have to go back to the start. When the groups store the possible states of the rows and columns in their qubits, the quantum computer allows them to assign a plus sign or a minus sign to each of the realities. You can think of these like positive and negative numbers, in the same way that you can add a -3 to a +3 to get 0. When 2 realities with opposite signs come together, they annihilate each other, like matter and antimatter. Before the game begins, the group agrees to put a minus sign in front of every reality with a 1 in the top square of the column. Going back to the 8 winning realities that we saw earlier, we see this set of signs. Now, when we look at the 0, 0, 0 row, blue can distinguish between the 2 different realities for red's column. For one, they see the 000 state, which is linked to the 001 state for red's column, and for the other, they see -000, which is linked to the 100 state for red's column. This is enough information for blue to update their row to match any row that the referee might choose and still win. Let's see how this works in an example. If the referee chooses the bottom row instead of the middle one, leaving the middle column unchanged, here's the strategy that both teams agree on in advance. If a reality has a minus sign, nothing needs to change. The intersecting digits already match these cases. For the other realities, the recipe is simple. Blue just has to flip the state of their first and second squares. This doesn't just work for the 000 row, but for each of the 8 realities. In the same way, a set of updates, like flipping the first 2 squares in the row, can be found for each possible choice of the referee, so that the resulting 8 realities are always...
Okay, so did everybody understand that? Yes, great. Hems, I hope you're still watching. Hems Thakrar, you're a software programmer, and you would think, what a load of rubbish that was. Because, thank you, Hems, he's still here, amazing the possibilities, and you're so right. I always say to young people, learn this stuff now, and you will have a challenging, professional, highly paid career for the rest of your life. Because people like Hems, people a little bit like me, although I've never been a programmer, you have to learn everything again, because it's totally different when you're doing quantum programming, because it's crazy. Let me now explain it the best. Oh, Amanda, yes, you have to be quick because I just noticed. Yeah.
It just makes me wonder about the bridge between the two of them, because the classical software programming and all the stuff that we are operating our world with now needs to keep going as like transitioning, etc.
But there are interfaces being written here in Australia as well. Anne knows about it. But let me try and explain this at a very basic level. And I do want to add, let's all stay in touch, because we can do the same thing next week, and I'll explain this in greater depth. Because if you don't know any of the terms, you're not going to understand it. Quantum particles have two amazing, well, they have many amazing properties, but they have two amazing properties called quantum entanglement and superposition. Now, in an experiment that, being done millions and millions of times, called the double slit, it was proved that a subatomic particle has this thing called wave particle duality. It is in superposition. Nothing you've ever encountered ever in your life is like this. It is, we talk about, when at school you learn that the electrons, which is a quantum particle, orbit around the nucleus rather like the Earth orbits around the sun. And that is simply not true. Because with a subatomic particle, there's a thing called Heisenberg's uncertainty principle, which goes back 1925, where he proved, and it's right to today, been proved many, many times, you cannot know the location or the momentum of a subatomic particle. Now, because we haven't got the right depth of equipment, it's like nature is not allowing us to look into superposition. We're not allowed to examine it any further. But it basically says a quantum particle can be in a million different places at once. It has a probability of being in those places. You can't say it's there. It is in a probability wave. And And even more amazingly, when we try and measure it, observe it, it's called the observer effect. When you try and measure a quantum particle, it suddenly becomes something distinct. It is in one place, it's quantized. It's in a place, we can do the momentum, it becomes an ordinary particle. But if you don't watch it, it will carry on in an infinite number of probabilities. And we can measure this stuff, linear algebra, which is unbelievable. The second thing is if that's not enough, we've got quantum entanglement. Two subatomic particles, one here, and I entangle them, which is an easy process. I get one here, and I get one on the moon. And this is a subatomic particle, a million times smaller than a speck of dust. If I get one here, and I send the other one to the moon through fiber optics, normal way, and then if I push the one on Earth a little bit to the left, the one on the moon will move a little bit to the left. Now, we can't explain it. It's been proven many times. You've got entanglements and you've got superposition, which are really weird. Quantum teleportation is something I lecture on all the time. And that has already been done. You know, we have the Chinese 5 years ago teleported something from the Earth to an orbiting spacecraft instantly. Now, let's get back to the game. So I'm only going to tell you what happens. Believe that what I've just said is true. Then what happens when we play the game, instead of having a row, we still have a row. We have 3 qubits instead of squares. We have qubits, and these qubits are subatomic particles in this strange superposition. Now, when the referee rolls his dice and he says 4 and 6, or no, he doesn't. He says 1 or 2 or whatever. We now, and that refers to a certain qubit, and those qubits are entangled. Now, there's else I should have said. Each one of the qubits has what we call a Hilbert space. All of the possible combinations exist on every qubit. Now, I'm not saying, they actually exist. Like Schrodinger's cat is dead and alive. These are, in every single, I think there was 64 combinations here. There's probably, we're actually, each qubit is in a superposition of everything it can possibly be. Now, when the referee throws the die, and he then hones in, if you like, on those 2 numbers, and those 2 numbers together reflect the intersecting square. Because everything is in the probability of being everywhere, you can concentrate on the intersecting square, and you entangle those that form the intersecting square on the rows and the intersecting square on the columns. There's 1 in each, and you entangle them. And when you entangle them, they will always give the same result. There will always be 1 or 0. So straight away, you may remember, if you understood a bit of the video, straight away you're down to 8, where you're automatically going to be right. But then there are still 8 combinations from the referee where you will be wrong. It won't follow the rules. Now, remember the plus and the minus? That's simply a phase shift. If we're talking electrons or photons is a particle of light. It has polarization. You can have it positive or negatively polarized. So that minus, the phase, is minus, and that can be detected. And when that is in minus, it then goes to the other two qubits and performs a quantum gate, which is called a Z gate, and that flips them, and you will always win. Wow. Any questions? Oh, actually, I might just answer the Facebook user group. How was teleportation measured, observed if the double slit experiment findings mean the observing world would interfere with the result? Teleportation is done mostly through entanglement rather than superposition. You still need to communicate. They have a bell pair, like in the game when the referee says 1 and 3, those two are entangled in a bell state. And in teleportation, you have them in a belt state. So you can't just teleport anything anywhere. You can only, and you have to prepare a belt state first and then send the other one. It could be on Voyager now, so it could be out of the solar system. But you've got to, you know, you can only teleport with those two qubits. And you also need a classical bit to collapse the wave function. When you view a subatomic particle in superposition, it collapses. So in teleportation, you're collapsing.
Will the internet be affected by quantum computing?
Oh my God, yes. Oh my God, yes.
In how?
Oh, in the fact that it will be instantaneous. Because let me tell you the most important thing straight away. For the first time ever, we will have 100% security. Now, that might not sound like a lot to you. That is killing everybody. It will kill cryptocurrency. It will mean that the dark web, which we now find out because we can decrypt it, it gives the uncryptable code. When I did my...
Put Cisco out of business?
Oh, well, yeah, they'll have to change. Everybody's going to change. To get back to the internet, though, but when you use an ATM, the fastest computer on earth that does 200 quadrillion operations a second would take 3,500 million years to get your PIN. A quantum computer can get your PIN virtually instantly.
No, just trying to get my head around it, Eamon.
Yeah, I mean, we will have follow-on sessions from this because if you should want to know how this works, and believe me, I can explain it to you. I just can't do it in 10 minutes. Lorraine?
No questions for me. I'm still and trying to digest it all.
It's difficult. But Lorraine, I'm serious. This is something you will be able to program if you keep on with Kiskers. You'll be programming as if it was nothing in a decade. Think so? But you really will, because there will be a pull down graphic that does the whole teleportation, the whole this. The important point I want to get out to all of the audience out there, and thank you for your contributions. This is defying logic. The game we played before cannot be won. Yet, with what I explained very quickly to you, we will be able to win every time forever and instantly. And we can write programs in business that have this unbelievable, inexplicable, well, I was going to say logic to it, but there's no logic.
Some projects or questions or problems that are better suited to a classical or traditional computing. And there are some questions, problems that are better suited to a quantum solution. And so what, for example, we're doing at Posi is we're trying to blend that, right? So where a question is better answered in a traditional use of supercomputing or computing, that is done, and then a subroutine, if you will, goes out to do what is appropriate for quantum computers to do, feeds that information back in. So I don't know that there's going to be a massive getting rid of everything in quantum computers taking over the world.
Oh, no.
I think there are things that are better suited, and those are things that, as we're seeing here, there are many, many answers. There's many, the traditional one is the traditional classical, we don't want to use those words. A typical problem that is solvable by a quantum computer is the traveling salesman, because they have to make a number of stops, and there's many configurations as to what would be optimal. That's a really good quantum challenge. So is a business portfolio, right? Like there's many, many ways that you can do a portfolio. So finance computing, quantum computing makes sense, but not everything makes sense.
Look, it is 7:45 now. We probably should wrap it up for the people at home. I'd like to thank all the panelists. You've been amazing. So it's fantastic. So let me say goodbye to everybody. Thank you to the panelists, and let's stay in touch, and we can go one huge step further next week. Thank you all.
Thank you.